You have fallen into Event Horizon with John Michael Godian. John is joined today for a special exclusive interview with Professor Nikku Madhusudhan. Professor Madhusudhan is a professor of astrophysics and exoplanetary science at the Institute of Astronomy at the University of Cambridge. He is widely known for pioneering atmospheric retrieval methods for exoplanets, along with various theoretical and observational developments in the field over the last 2 decades, and for the conception and development of the Hycean paradigm in the search for life elsewhere.
Dr. Nikku Madhusudhan, welcome back to the program.
Thanks, John. Glad to be back.
Now, Doctor, the last time we talked, we were talking about the exoplanet K2-18b, and this planet is interesting for not only your work, but interesting to a lot of other researchers because this is a habitable zone exoplanet that has an atmosphere inside the habitable zone of a red dwarf. And there's been much talk over the last 5 years about red dwarfs being uninhabitable stars because they might strip their atmospheres from exoplanets. But this one appears to have one.
Exactly.
But we don't entirely know if this is a Mini-Neptune or if it's a terrestrial world.
Yeah.
So where's the state of characterizing what this planet is like, this exoplanet, at this point?
So the mass of the planet, just to summarize, just to start with the very big picture, the planet is 8.6 Earth masses in mass. It's roughly 2.6 Earth radii in size and is in the habitable zone of its host star, as you said. That means it receives roughly the same amount of total radiation that the Earth receives from the sun. So if you were to put like a terrestrial planet there, you would assume it to be potentially habitable. Now, this whole star, red dwarf star, could it be active? Could it strip out the atmosphere? There are all those caveats if it were a rocky planet. But nevertheless, that would be in the habitable zone. Now, given the mass and radius of the planet, it's too big to be a purely rocky planet. If you take the density of just a rocky planet, this planet is lower than that. Its density would be consistent with an entire water world, but won't be consistent with a rocky planet. But given that scenario, that situation, a lower density than a purely rocky planet, there are 3 types of interior compositions that can explain these bulk properties. One scenario is what people have said in the past is a Mini-Neptune scenario, which means you take Neptune and say this is a miniature version of Neptune. What does that mean? Neptune has a radius of 4 Earth radii and a mass upwards of over 15 Earth masses, more like 17. So this would be, in the Mini-Neptune scenario, a miniature version of Neptune. That means the interior, you can have a rocky core in the very interior, but much of the interior surrounding the core is composed of ices, high pressure ices, okay? Now the ices could be a mixture of ice and rock, but like more of the volatile material, water ices or other kinds of ices. And then it has a thick hydrogen rich atmosphere. Now how thick? It could be thousands of bar in total pressure, the atmospheric extent. So a thick hydrogen rich atmosphere. That is a Mini-Neptune scenario. There is another scenario called a gas dwarf scenario, which is where you remove the icy mantle in between. So you have just a rocky interior and a hydrogen rich envelope. So it's just rock and hydrogen. So that would be a gas dwarf scenario. That's what they're called. So those were the 2 prevalent scenarios that people had thought in the past. And then there's a third case, which is a water world. So which means the interior would be predominantly watery. So you can still have a rocky core, but a water rich mantle, but a thin hydrogen rich atmosphere such that there is a chance that below that atmosphere, you could have liquid water on the surface. It doesn't have to be habitable because the liquid of water can also be much hotter than what is conducive for life here. But nevertheless, you can have liquid water. That's one scenario. So these are three scenarios that have been considered in the literature, and all three scenarios, these are different combinations of rock, water, and hydrogen that can all explain your bulk properties, the mass and radius of the planet. And the reason we need to invoke the hydrogen-rich atmosphere is because observations have confirmed that the planet has a hydrogen-rich atmosphere. So for example, for that reason, it cannot be a pure water world with a steam atmosphere. You need hydrogen, but it has to be a thin hydrogen rich atmosphere if it has to be liquid water. So these are three scenarios that explain the bulk properties, this mass and radius of the planet. But then how do you distinguish between these scenarios? Now, this third scenario that I mentioned, this water world with a hydrogen rich atmosphere, the water being habitable, is also what is known as the Hycean scenario. The Hycean stands for hydrogen and ocean, hydrogen rich atmosphere and an ocean covered surface. Now we have these three scenarios. How do you distinguish between them? What data will allow us to break the degeneracy? And that's where your atmospheric observations come in. So before even the observations were made, the last time we spoke, that was in 2023, we made those observations. Even before those observations were made, there was a prediction for how you would tell between the three scenarios based on atmospheric observations. Now, what is going on there is that if you have a deep hydrogen-rich atmosphere, then the chemistry there would basically be not very different from what you would expect in a cold Neptune. So Neptune, for example, has a lot of methane, obviously, and ammonia in its atmosphere. Okay. So you would also expect this planet, K2-18b, because it is also cold, its equilibrium temperature is below 300 Kelvin. So the atmosphere can go to freezing temperature. So it's cold. So you would also, if you had a deep hydrogen-rich atmosphere, you would expect the atmosphere to have a lot of methane, a lot of ammonia. And you can also have carbon monoxide because the temperature profile, if it's a deep atmosphere, the temperature is increasing as you go down the atmosphere because of the greenhouse effect. So in the deep atmosphere, you make a lot of CO, carbon monoxide. So by vertical circulation, you end up having observable CO in the upper atmosphere. So there is a prediction that if it is a mini-Neptune, you expect to have a lot of methane, ammonia, and more CO than CO2. So the CO over CO2 ratio you expect to be comparable or greater than 1. So those were the predictions. But if you had an ocean underneath, then and that prediction is the same for a gas dwarf or a mini-Neptune because both involve a deep hydrogen-rich atmosphere envelope. But the difference when you have this Hycean scenario with an ocean world and a thinner hydrogen-rich atmosphere is that the presence of an ocean and the fact that the atmosphere is thin means that it cuts off some of this recycling of material from the deeper atmosphere to the observable atmosphere. I'll expand on it a little bit more. When you have a deep atmosphere, this methane and ammonia, for example, could be destroyed in the upper atmosphere by photochemistry. But because you have a deep atmosphere, these molecules are readily reformed in the bottom atmosphere, and you can circulate them, transport them from lower to upper atmosphere, and you can still observe them. But if you have an ocean that cuts off that circulation and the atmosphere is shallow, then over time you lose these molecules. Like you could lose methane, but you could definitely lose ammonia because the ammonia is more easily destroyed. But also, ammonia is soluble in water. So the prediction is that if you have an ocean underneath, the ammonia would be soluble in the water, so you wouldn't see ammonia. You could still see methane. It could be some remnant methane from formation, although that is also susceptible to loss. But it could also be, if you have biofluxes, life on the planet, you could also have methane from the ocean itself. And then the second prediction for an ocean world is that you would have more CO2, carbon dioxide, than carbon monoxide, because remember, the carbon monoxide came from the deep atmosphere, which in the case of this ocean world doesn't exist anymore. So those were the predictions before the previous observations. Now, when the previous observations were taken, the 2023 observations, we found that we had this discussion before, which is we found methane, we found carbon dioxide, but we didn't find ammonia or carbon monoxide. That is a pattern that was exactly predicted for a Hycean scenario before the observations were taken. And it's not even us who predicted that first. There were multiple groups, other groups, that had made those predictions. We did our own calculations to verify those predictions and we agreed with them. So there were 3 or 4 papers around that time before the observations, those predicted. Then we did the observations and then we said that, look, I mean, this was what was predicted and the observations agree. with the Hycean world scenario. So that's the state of the play, was the state of the play when the last observations happened. Now, after that, in the last 2 years, there have been several papers that came out proposing alternate hypotheses, saying, oh yeah, no, it can still be a mini Neptune by playing with some of the parameters, model parameters. That was one. There is this recent paper, Wogan et al., that gets cited for this mini Neptune scenario, where they said that they can explain all the observations with a mini Neptune scenario. But when you look at the actual predictions from their model and you plot the observed abundances next to it, and we did that in a recent paper with one of my postdocs, we found that they had never actually compared their models with derived abundances in our paper. So that sort of told us that we showed across a wide range of parameter space that you can't actually explain the Mini-Neptune scenario, explain the observed abundances with the Mini-Neptune scenario, because they don't match the ammonia or the CO2 over CO ratio. That's one thing. Then there was this other scenario that gets quoted a lot. Sometimes people say these magma oceans, because magma oceans, and this has been known for a long time, that ammonia is also soluble in magma oceans. You will hear this argument quite a lot in the literature. Again, we investigated that, and what we found that basically they ran a grid of models for that, but basically every single model that was reported in that paper was physically implausible. For example, they forgot to check for mass balance. So they forgot to check that the total mass of the mantle plus the atmosphere should equate to the planet mass. So they just didn't do that. And that makes the model incompatible, intrinsically incompatible, not just with the data. The model itself is physically incompatible. Same with density, for example. Many of the models violate the density constraint that we have. So even if we put that aside, what we found that there were several such model inconsistency, but the bottom line is that model didn't explain the observations either. And then they say that they even admit that doesn't explain the CO2 over CO ratio. So there are a couple of explorations like this, but we ourselves have looked at all those models, and the state right now, and this could change in the future, obviously there could be some other model that could come up, but currently the state is that you need a lot of water in the interior no matter what. There is the most likely explanation currently to explain all the observations, even without the DMS. I'm just talking about the methane, CO2 observations and so on. Currently, the only model that can explain all of those abundances is one where you have this Hycean world scenario. Now, we don't know whether this is actually habitable. I'm saying it's a Hycean world scenario because you can explain those abundances, but you can do that without being habitable. The water could be too hot to be habitable, so it doesn't have to be a habitable world, but it still needs to have like a thin atmosphere and a large water component in the interior. That's the only model that actually works. Now, the open question is whether that water is habitable or not. So that is the current state of play. And with the new inference, now that we have DMS, again, we are open. This is only a borderline 3 sigma inference that we have. That is pretty good in terms of being interesting enough to continue looking into it, but it's not robust enough. So we are open to that changing. But if that is true, then the only situation that based on current understanding can explain all these observations like inferences including DMS is one where the planet is actually habitable and maybe even inhabited. So that is the current state of play based on existing literature.
Now, I guess the natural question is, all right, so in these other scenarios where it is not a Hycean world, not an ocean world,
right,
you would expect from a volcano planet with a mostly molten surface to have a gas profile that has things like hydrogen sulfide, sulfur dioxide, all of those sorts of things.
Yeah.
Can JWST see those in the infrared spectrum and sort of knock that out or confirm that it may not be a Hycean world, or isn't one yet? For that matter.
Absolutely. You're absolutely right. If there is volcanic activity, you expect to see sulfur species like H2S, SO2, and so on. And JWST does have the capability to detect those. Those have strong features, and it has been detected in giant planets, for example, some of those molecules, and even in a smaller planet, rocky planet, there are inferences of those at least one of those molecules. So yeah, so we have observations and the sensitivity to detect those molecules, but we don't detect them.
But you do detect hydrogen disulfide, or not hydrogen, rather
Dimethyl sulfide.
Biogenic
Yeah.
gases,
Yeah, dimethyl
and
sulfide. Yeah.
yes, and we don't see our volcanoes here on Earth producing those.
No.
So dimethyl sulfide and dimethyl disulfide, these are unique gases, and it seems to me, looking at the spectra that you took, which is a 3 sigma detection, which is good enough for most astronomy, better if you can get it to 5,
Right.
which is the particle physicists,
Right.
that's what they like,
Right.
which is what you're going to do. We'll get into that in a bit.
Right.
But this is a solid detection. This is better than a hint, right? This is enough to swing the Webb telescope towards this and take another observation.
Absolutely.
Now, what was the process? How did that happen? After the last paper that we discussed here.
So the last paper, we saw those carbon-bearing molecules, and we just saw a very, very tentative hint of DMS, and we didn't make much of a claim about that. But then we went ahead and looked at the planet at another observation with the MIRI spectrograph. MIRI, so the previous observations were between 1 to 5 micron. Okay. Now, this new observation is between 5 to 12 micron. So more precisely, I mean, the data that we actually use is between about 6 to 11 micron, which is where we think that the systematics are stable and well, we understand them well. So we are erring on the side of caution, and we just took like the roughly 6 to 11 micron range. And what we found was the result that we have in the current paper is that we see evidence for at least one of two molecules, dimethyl sulfide or dimethyl disulfide. Now, before getting to that, the process is, I mean, the technique is the same. Should I go over the technique, the transit method, or we can just assume the spectrum is known?
Now, in this case, all right, data pipelines and analyzing the data.
Yeah.
What did you go through?
Yeah.
How many different processes did you go through to confirm this?
Yeah, no, yeah. So for this conversation, we'll just assume that we know what the transit method is. So we get a spectrum when the planet goes in front of the star, starlight passes through the atmosphere of the planet before reaching the telescope, and you get the absorption in the planet's atmosphere. You get that spectrum. But the data pipeline involves, this is JWST data we are talking about, and MIRI is different, is slightly more challenging than the other instruments. And there are various steps in that data, how you go from the raw data to the chemical inferences, right? So first you have to convert the raw photons on your detector into what is known as a spectrum, the stellar spectrum that you're observing. And then you have to convert the stellar spectrum, and over time that you're looking at this time series observation, into a planetary atmospheric absorption spectrum, which is known as the transmission spectrum, by fitting light curves to each spectral channel. So there are a number of variations in the data choices that you can make in the data reduction. All the way from how you go from the raw counts on the detector to like a flux value. You have to correct for various nonlinearity effects. You have to correct, for example, for trends in the light curves. When you're fitting these light curves over time, you will see that for MIRI observations, there is a ramp that appears in the beginning. You have to fit for that. That is an instrumental systematic. That's not an astrophysical signal. You also have several choices you can make for the limb darkening of the star when you're fitting for the transit. So there are a number of these assumptions that you could be making while doing the data reduction, all of which can impact your spectrum in theory. So our approach actually was to say that I'll go over the experience, the personal experience that we went through this whole process. But at the end of that, the summary is that we went through a lot of different combinations for each of those, a lot of different choices we could make for each of those processes. And we did some very serious robustness testing at each step and blind testing. So do you want me to, John, go over like the manual side of it, how we actually implemented them, the blind testing?
Absolutely.
Okay.
Yep, go for it.
So even before we looked at the data, what we said is that we have to build a robust pipeline from scratch. There are pipelines available online, but we said let's build our own. So we are not using something just box standard without knowing the intricate details. So we just went ahead and built something completely from scratch. And we basically took almost every MIRI spectrum of an exoplanet that was out there in the literature at that point, or all the published ones at least. And we reduced all the data. So these are the things that happen behind the scenes that you don't see in the paper, but this is for our own internal robustness. So we do all that and we reduce all the data that is published. We reproduce all the results that are published. And then we said, let's get the pipeline to a stage where we don't have to look at anything specific for this data set. Okay, so we shouldn't be able to tweak anything in our pipeline after we saw the data, because we might be biased in doing that. So we created a initial version of our pipeline. I went ahead and did a quick run on the spectrum, and almost on first trial, we were seeing some features immediately. And that was a moment of both excitement, because we hadn't expected that even in MIRI we would see features, because we expected the signal to noise to be a lot higher, and it was higher. But we were seeing features because the features from the planet were inherently much stronger than we had expected before. So that there was a combination of that excitement that we were seeing something, but there was also the extreme caution that this could have the potential of something impacted by systematics, right? By unknown instrumental systematics. So we quickly said, let's not look at the spectrum anymore and start like extreme blind testing, more testing of our pipeline before we could do any interpretations of this. So we created two separate efforts, completely blind efforts. So two of my collaborators individually with two of my collaborators. And then in each case, we ran an entirely different pipeline, neither of the effort knowing what the other effort is doing, and going through each of those steps that I described earlier of the data reduction to make sure that every single step, we try multiple different options and check the robustness. And at the end, I'll cut the long story short, this was months. This took months for us to do because we are basically replicating everything blind from scratch. And after a few months, we put all the data together, the first version that I created and the two blind versions later that we created, all these three we plotted together. And amazingly, they all agreed to within the uncertainties. So to us, that was the moment where we finally thought, okay, we are actually seeing something real. Okay. And one can argue that the data is still not like extremely precise, but you can see the features by eye, right? You have the spectrum in front of you. Everyone on the internet has the spectrum in front of them. You can see the spectrum and you see those wiggles by eye. And when that happens, you know that it is not a complete fluke, what you're seeing. And then we went through a similar robustness test with independent retrievals that we have done. Retrieval is the process where you take this data set and try to extract the composition, the atmospheric composition from it. So we did other independent retrievals to again extract the chemical composition from the data, and then we picked up these molecules. So that was the full process. So we are actually quite proud of our robustness, and all said and done, when we have the inferences that we have today, we are happy with what we're quoting. We are saying for the canonical model that we finally came up with, we are seeing about 3 sigma confidence. In some cases it is more, in some cases it's like borderline 2.9, but these evidences, these sigmas have an inherent uncertainty of 0.1. So we rounded off, like across all the cases, we rounded off saying we are happy to consider this as a 3 sigma detection, even though in most cases that we tried, it is slightly above 3 sigma, but that doesn't matter at that point. It's roughly 3 sigma is what we would say. And we're happy to be, if someone else comes and does it and they find 2.5 sigma, that is fine too. But we're happy with where we are right now.
Now, when considering this signal, it's important to note here that these are 2 different instruments on Webb.
Exactly.
And that means that this is an independent detection if you see it in 2 instruments. And the first instrument from the first paper was 1, and the second is the other. Actually, 3 instruments, I think, are involved. Explain that. Tell everybody why different instruments looking at this can even do this with Webb.
Exactly. I mean, I'm glad you asked that, but because this is an often overlooked part, it's a subtle point, but it's very overlooked, is that, yeah, the previous observation has nothing to do with this observation. That's on purpose. We did not use any information. Usually, when you have one detection, you build upon that by adding new information to it. But we said, let's have an entirely independent line of evidence, not take any information from the previous observation. So just this MIRI observation alone, we tried to search for 20 different molecules. Now, why 20? That is the largest number of molecules ever predicted for this planet and searched for this planet or planets like this. And we wanted to be thorough. We wanted to take not just the molecules that we considered previously, which was about 11 molecules. We added more molecules that had been predicted in the last few years since the first observation. And we did this, including all the sulfur species that you were mentioning. And we didn't find anything but just one molecule in the first instance, DMDS. And if we removed that, we found DMS. So we said these are the molecules that we need to consider. We also added the previous inferences, CO2, methane, and together we constructed a canonical model. And we tried to look for all those molecules robustly with a different instrument like MIRI, as we are discussing here. And we found that the signal is so strong of these two molecules. It can be one or both of these molecules because there is a degeneracy. There are overlapping features of these molecules, so we can't tell them apart entirely. But the features of these molecules are so strong that they drown out all the features of methane that could be present in the MIRI band in this wavelength range. That is amazing if you think about it, because that is the only reason why we are even able to detect these molecules. Otherwise, when we were proposing for these observations originally, we hadn't expected the signal to be that high.
You wouldn't expect that, no.
Yeah, no, we didn't. So that to us, like the additional confidence that when you're looking at it with a different instrument and you're finding a signal that strong, yes, statistically it is 3 sigma, but the physics behind it has to be so well constrained for you to be able to even see these molecules in the first place.
Now, the chemical process of producing, if this is indeed signatures of dimethyl sulfide or dimethyl disulfide,
yeah,
we know that when we look at Earth, we know that it is life creating this gas here.
Yeah.
Both gases, actually, which are intimately related, but
right.
These things do not last long, meaning that they have to be replenished. They are in disequilibrium,
yeah,
which is important for exoplanets. When you're talking about
yes,
astrobiology,
yes,
gas disequilibriums are probably the most important thing for a biosignature.
Right.
And when you look at Earth, you see the disequilibrium of oxygen.
That's right.
You know? But here we're seeing a disequilibrium.
Yeah.
Now, it's always going to be argued that, well, maybe there's an abiotic way outside of biology to produce dimethyl sulfide.
Right.
Well, that means you got to go in the lab.
Right.
And and I have to point something out here. We're detecting this at 124 light years distance. So this signal, you're going to need a lot of this gas to see it at that distance. This isn't a trace.
Right.
This is a lot.
Right.
So you need a very robust chemical process to produce all of that. That is very, very efficient, very powerful. If this chemical is there, what do you do in the lab? What's next? How can you test if there are other alternative ways to produce dimethyl sulfide? Because some people have made the argument over the last few days that, well, we haven't studied it very much, but that's a big chemical process to miss if you can see it in the atmosphere of an exoplanet over 100 light years distance.
So we fundamentally want to remain open to the unknown unknowns. So in the future, someone could come up with a lab experiment. We ourselves will be looking at various theoretical pathways. It is possible in the future someone may come up with an abiotic process. But let's talk about what we know right now, right? So currently, there have been some experiments that have been done in the lab. There have been experiments even in the 70s, people knew some things. And recently also, there have been some experiments done to make these gases in the lab. So if you have a mixture of H2S, of high concentrations of H2S and methane, and you have electric discharges, you can make, in principle, these molecules in the lab, okay? However, the problem with that is that both the molecules, as you pointed out earlier, have very short lifetimes. So even if you make them abiotically, it is not clear in a laboratory setting, the lifetimes are very, very short. It is not clear how you could sustain those in a whole planet in steady state, okay, without a continuous replication of that process at large quantities. Now, the quantities I mentioned is the second problem, which is that the quantities we are seeing in this planet are thousands of times higher than what you see in the Earth's atmosphere. In the Earth, these molecules are present at about like a part per billion or less. What we are seeing is at least 10 parts per million. So that is over 10,000 times higher than what we see on the Earth. These experiments that we are talking about cannot make that much amount of these products. Now, the third problem is that even if they did, you expect to see the parent molecules, which is methane and H2S, you expect to see the parent molecules at higher abundance than the daughter products, the DMS or DMDS. Now we don't see H2S, even though it's very observable in the wavelength range we are considering. We don't see H2S at all, right? So there are various caveats like that which don't work with the experimental results we have currently to explain the abundances that we are seeing. So that's the problem. But as I said, we want to remain open. Maybe there is a way to replicate it in the future. But based on current experiments, the latest knowledge we have in the field is that that angle won't work to explain the abundances that we are seeing.
Now, with dimethyl sulfide, DMS, the fact is that we use this industrially. We can make it in the lab, but biology makes it.
Right.
And if you make it in the lab, it's artificial,
right. Exactly.
synthetic, and we use it as like a food additive. It's present in the human body, and it's, the microbial life really likes to produce it. So what this is pointing to is a potential. We're at the very beginning here. The potential of a microbial biosphere. This could be algae. And it could be floating in an ocean and doing its thing, but it is doing it like big time, as you pointed out. It's much, 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 much higher than Earth. Could Earth, looking back in time, before the great oxygenation event, before we threw all that oxygen and, life threw the oxygen in the atmosphere, this particular exoplanet does not appear to have that oxygen, but it's only 2.5 billion years old. It's a little bit younger than our system. Could we be seeing, with this potential Hycean world, a planet that Earth was once like, that is producing this? Are we seeing an early Earth here, perhaps? If, it's hard to say that and apply that to an exoplanet 8 times more massive than Earth, but still. Could this just simply be that we're looking at an early Earth, an earlier stage of life, and that we, as we debate about it, we might not recognize it completely, but we wouldn't have recognized Earth this way either?
That is a very interesting point, John. I mean, you picked up a very, very important and subtle research level point, which is this is one of the things that we have been thinking about and working on, which is that there have been papers written, like when DMS was first predicted as biomarker for exoplanets. This is going back more than 15, like over the last 2 decades, several studies have predicted that DMS and DMDS would be like robust biomarkers. And one of those studies actually said that if you looked at the early Earth, these would be the most promising biomarkers before oxygen became abundant, which is basically the point you're making. And I mean, it's very interesting for me to see that you picked up that level of detail, because that was the original motivation for predicting these molecules, in that early life, which is microbial in nature, would have produced a lot of these species, and those would be very robust biomarkers. And some of those early life, especially simple microbial life, still exists in like that nature of life still exists, and those are also producing the same molecules. So in a hydrogen rich environment, oxygen won't be a good biomarker because oxygen would react immediately with hydrogen and form water. Okay, so even if there is oxygen released, it would be very unstable in a hydrogen-rich atmosphere like of this planet. But these molecules, DMS and DMDS, if you see them, they would be good biosignatures because they can still be like similar to Earth's atmosphere. They're very unstable, but they could still be observable in a hydrogen-rich atmosphere.
Very stable.
I mean, stable in the sense, stable at the level where you can observe them. They would still be unstable on like 1 day timescales or so on. But if you have a continuous replenishment of these species, you can keep them more stable than oxygen, for example.
Yes, but that puts a burden on the idea of, all right, well, how fast can you replenish it?
Yeah, exactly. So I'll tell you one more fun fact. Just before these observations last year, actually, there was a paper written by a different group hypothesizing, like they were investigating how much flux do you need from biology of DMS or DMDS to have the kind of estimates we are talking about, let's say 10 parts per million or higher. And they put an estimate at around like 20 to 30 times Earth bioflux, Earth sulfur compounds, to get these levels. And our observation basically confirms like those sorts of levels, which means that if this is indeed like true, if we are actually finding DMS and DMDS, and if it is from life, then you expect 20 to 30 times more active bioproduction of sulfur-based gases compared to Earth. So the surface would be teeming with microbial life if this is indeed due to life.
Now, back to the lack of oxygen. How well is that characterized? In other words, it is said in the literature that they didn't detect oxygen, and that would suggest a situation where photosynthesis is not occurring. Yet at the same time, what I'm really asking here is, can non-photosynthetic life, very simple life, produce these gases without a problem? Because Earth life didn't produce oxygen for its first billion years, something on that level. Is this consistent with life that has not yet hit photosynthesis, which of course there's no guarantee that life on an exoplanet ever would hit it? Simple life.
Yeah.
So
Yeah.
could you characterize that?
Yeah, no, absolutely. So we wrote a paper earlier this year actually talking about evolutionary rates, a rate of biological evolution on Hycean worlds. And we talk about this sort of aspect that a lot of microorganisms do release these gases in a anoxic environment. So you don't need like an oxygen-rich environment for these gases to be produced. And again, this goes back to the early Earth scenario where these gases were produced even before oxygen was abundant. So it is consistent in that sense.
In that sense. Now, let me ask you this, as basically the scientists that really proposed Hycean worlds.
Yeah.
Can a Hycean world of this mass, a big one?
Yeah.
And a lot of people have tried to make the case over, again, the last decade, that anything over 2 Earth masses probably couldn't produce biology. But I would say that we don't know that for microbes. Can a Hycean world constrict life and keep it at a microbial, non-photosynthetic state?
Yeah. So the only reasonable argument I have seen people make, and I don't think this is well explained in the literature, that for a Hycean world, the lack of a landmass and just water everywhere is an argument people make that may be difficult for life, lack of a surface. But as we have been thinking, we don't see that to be a particular issue because the early Earth was mostly water and forming life should not be a problem. But then we don't even know how life originated here on Earth. So that in my mind is an open question that we may not be able to fully answer at this stage. At least it's not answered in the literature. But sustaining life is not the problem. So once you solve how life began question, which is an open question here on Earth, once you start it, then sustaining it is not a problem in a Hycean world because we looked at what kind of resources, bioessential nutrients, for example, that you need. And we established, and this is again published literature, that you would be able to sustain, give the ocean enough nutrients just from external sources by impacts, for example, and just atmospheric precipitation of key minerals. That is not the problem. Sustaining is not a problem. And in fact, when we looked at biological evolution rates for Hycean worlds, And this is an interesting calculation. If you just increase the temperature of the Earth by 10 degrees, the biological evolutionary rates all go very, very fast, and the production of these gases also increases. This is just last couple of months ago we published this work, but the slightly higher temperatures in Hycean worlds basically makes the production rates even faster. So from that point of view, sustaining life itself is not an issue.
But the question that sort of sticks in my brain is that because you're dealing with an exoplanet that is so very different from Earth,
right,
and around a different type of star, is it
right?
Can that limit life? In other words, this may not ever be able to produce an intelligence, for example, because that intelligence is either locked in an ocean.
Absolutely.
You know, if it can form at all, it's locked in an ocean under very high gravity, and it can't ever leave its gravity well, and all of those sorts of things. So would it be reasonable to expect that we live in a largely microbial universe if Hycean worlds are the rule that are much more massive than two Earth masses?
Yeah, I mean, mass is not a particular issue. It's usually the argument that's made is about gravity. And the gravity of this planet is not that high either. It would be like over 20% more. But we don't think that mass in itself is a problem as long as you have a habitable ocean. That is our current understanding. But obviously, all these questions of how life formed here on Earth, what are all the requirements around it in the very early stages? I mean, we don't know that, right? I mean, even on Earth. So those are open questions right now that we need to tackle. The one question that is more addressable is what you hinted at, is that the star being a red dwarf. Now, what happens is that as you go to lower and lower spectral types, later and later spectral types, which means lower masses, the stars become more and more active. So for example, if you go to a late M dwarf, that's about, let's say, 0.1 M solar masses, so a tenth of the solar mass, then those stars tend to be extremely active, and they can strip off like entire atmospheres if there is a rocky planet next to it. But if you're at the earlier spectral type, like around a half of a solar mass, like K2-18, then they're not that active. Yes, they're somewhat active, but they're not that active. Plus, if you have a large enough planet that can also hold on to its atmosphere better, and we have evidence, we are seeing a hydrogen-rich atmosphere that the planet obviously held on to. So atmospheric retention clearly has not been a problem for this planet.
No, it's right there.
Exactly.
And that's work independent of what you're doing, is that characterizing different gases in the atmosphere of this world, such as the hydrogen, shows it has an atmosphere.
Exactly.
Now, of course, that's going to be mass dependent to a certain degree, but hydrogen is hard to hold on to.
Exactly.
And it gets stripped off by solar radiation. But the thing is that this 2.4 billion year old world has it. Mm-hmm. We see it. Mm-hmm. It's in the spectra, and that's independent of your work.
Right.
So this shows that the question of the habitability of red dwarfs, which are by far the most populous star in the universe, actually is more complicated than we thought. So maybe, as you said, it's a sliding scale. Instead of them all being atmosphere strippers, some of them may not be. And so when you look at exoplanets like the TRAPPIST-1 system, and you don't see atmospheres in the first two members, that does not mean that a more massive red dwarf is going to behave the same way. And there is some question on how those things flare, that they may not flare at their equators as much. And again, that may have to do with mass, because you're dealing with fully convective stars that can live for trillions of years as opposed to the sun.
Right.
There is an idea out there, though, that statistically speaking, and there are two parts to this. And the first one is that it's the red sun paradox, as has been termed, that why is it we aren't around a red sun? A red dwarf, because even if this is only a subset of red dwarfs, that's still a lot of them.
Yeah.
But the second is that, all right, so Earth life is not around a red dwarf,
right?
But also we detected a biosignature, or a potential biosignature rather, just 124 light years away. That's close,
right?
Both of those taken together
Right.
would seem to suggest
Right.
that at least microbial life is insanely common in the universe. Am I making an error in inferring that?
No, that that is both the like excitement and the worry here. That if this is found to be true, if the molecule is detected and if we think it is from life, then yeah, that would be the natural conclusion that microbial life would be very common in the universe. You're absolutely right.
And I would wonder, it gets harder to blast material off of a planet the more massive it gets, right?
Right.
So
Right.
that eventually becomes a problem for panspermia.
Mm.
And it becomes a problem for an atmospheric density. What's the atmospheric density like with K2-18b? Does it appear to be very, I assume it has a pretty decent density for us to even see anything at this distance, but what's it look like?
Yeah, the we talk in terms of the total pressure of the atmosphere. Into Earth has a surface pressure of 1 bar, and we don't know what the because we see only the upper atmosphere. The deepest we can see is about zero point 0.1 bar. So we actually don't know what the surface pressure at the ocean is. But from theoretical calculations, we think it could be at max a few tenths of bar for it to be habitable, because beyond that, it becomes too hot to be habitable. So that's that. But also, the composition of the atmosphere is basically hydrogen rich, and with about 1% by volume each of methane and carbon dioxide.
Now back to atmosphere stripping. The idea that it's a red dwarf,
Yeah.
and it's going to have solar wind.
Mm-hmm.
Well, why didn't that alone strip off the atmosphere of this world? In other words, why didn't just the solar wind, like what happens with Earth, why didn't that strip the hydrogen?
Yeah, I mean it might still do, just not enough to strip the whole atmosphere. So even today there is some atmospheric escape happening on Earth and on all planets. It's just that it's not strong enough to strip the entire atmosphere of the planet. So what we are seeing is the atmosphere that has been retained after the stripping. So it may have started with a larger atmosphere, but more massive atmosphere, but it could have been stripped over its few billion years evolution, and what we are seeing is the remnant of basically what is left.
Now, water vapor has been detected with this exoplanet. How does that play into this? Does that support the idea?
So water vapor actually is not detected. It was with Hubble there was a claim of a water vapor detection, but in our last observations we found that that was actually methane, not water vapor. That is actually consistent with the troposphere being cold like Earth. For example, on Earth, at the surface, you see water vapor of about 1%. But if you go to the stratosphere, then water vapor drops by several orders of magnitude. The stratosphere is quite dry, right? Because the temperature becomes very cold. And the same is happening here, is what we think, is that in the stratosphere, we derive temperatures which are very, very cold, and we expect water to be condensed out, so we don't see it.
But methane in itself is a biogenic gas. Now, of course, methane has a lot of sources. Nature can produce methane all over the place.
Exactly.
Is it possible to assemble a profile of different gases in addition to DMS and DMDS? Is it possible to basically bolster the case that this might be a biosignature based on a much, much more full characterization of the gases insofar as we can detect with this exoplanet?
Yeah, interesting you asked that, because that is an angle that some studies have claimed before, including ourselves. So there are at least 2 studies which have explored that angle. So we do think that even like for rocky planets, this combination of methane and CO2 is a biomarker for an Earth-like planet. Okay, several studies have pointed this out. And we could use that argument here as well. But we just want to be careful because, as you said, in a hydrogen rich atmosphere, methane can be produced by some sources. It's not easy, but you can't entirely rule it out either. So we are not even considering that when we make the case for the possibility of life on this planet. But there is always that angle that is in principle a viable angle, the joint presence of methane and CO2 in significant quantities.
Getting to 5 sigma, which is your goal.
Yeah.
Getting this to a 5 sigma detection, which is basically, this is that either dimethyl sulfide or dimethyl disulfide.
Yeah.
Either one. Now, two-part question. First of all, how can you tell which gas it is? They're very, very closely related gases, and they're both biogenic, as so far as we know.
Right.
How can you tell that? And the other question is what further observations can you do with Webb, specifically, to get to that 5 sigma level? And can you do it? I mean, do you think, 3 sigma is enough to look again, I would imagine. So can you get more telescope time?
Yeah, no, absolutely. We make this case in the paper as well that 3 sigma is good, is very good in many cases, in the sense that it tells us that this is something worth pursuing further to the 5 sigma level. And in several cases, you can even make stronger statements about what you're seeing, but it is not the strongest. It's not the most robust. It's good enough, but like not the best. So as far as what observations are needed, we make the case that with just 2 to 3 more observations, exactly like the ones that we made here, MIRI observations, 2 to 3 MIRI observations, will get us to at least the 4 or 5 sigma level. I think they will get us to the 5 sigma level just with 2 or 3 observations, if the signal is real, right? So these multiple observations serve 2 purposes. One, it's the repeatability of the signal that we are seeing. So even if we saw exactly what we are seeing now, that is already a big deal if you see it 2 or 3 times. But in addition to that, if you combine all those observations, you get a higher detection significance. We will easily cross the 5 sigma for these molecules, DMS and DMDS. That's your first question. Answer to the first question. To the second question, yes, DMS and DMDS have significant overlaps in the MIRI range between 5 to 12 micron. But there are also regions in that wavelength range where they don't have overlaps. And if you get high precision data by combining 3 or 4 observations, you can distinguish between the 2 contributions. And that is how we would be able to tell whether it's DMS, DMDS, or both.
Now, independence. In other words, are there any other telescopes currently deployed that other researchers can use to confirm or call into question these observations of DMS and so on?
So currently, no. I mean, only JWST has the capability to look at this particular wavelength range and make these observations of this quality. So right now, it's only JWST. But I think where the efforts should go, in addition to the observations, is also theoretical, to just explore the unknown unknowns, so to speak. Because as you know, like there have been various claims for how people argue they can explain DMS without life. And currently, none of those claims actually hold. I mean, people do make these claims, but we can talk about it if you're interested. But currently, they don't hold, they can't explain the amounts we are seeing, but we want to look at those further as well.
My last question, which will probably get a little bit complicated, is now people have said that we see the presence of this gas in comets, but that was actually less than a 3 sigma detection, that paper, which is sort of a double standard. What are your views on that?
Right. Yeah. I mean, to the double standard, I will say that one thing I have realized when you do this sort of absolute cutting edge science is that the standard for the counter argument is always significantly lower than the standard applied to the main argument. So, for example, if you're claiming a detection of DMS, the standard that's applied is much, much higher than someone coming and arguing for another alternative. The standard there is much lower usually. That's what I've seen, but that's okay. That is healthy in the sense that it forces us to be very, 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 very rigorous for making any claims. So that's fine. Now, for the comet question in particular, yes, there was recently a claim of, as you pointed out, a tentative indication of DMS in a comet, and also I think in the interstellar medium. The problem, and some people use that as an argument, and we have gone to a good length discussion in our own paper on why that is not a viable mechanism currently. It's because comets are very different environments from planetary atmospheres. What's happening on a comet is mostly grain surface chemistry, right? So on the surface of these grains, icy grains, a lot of complicated chemistry can happen. You can form a lot of like complicated molecules, which then sublimate, and you can see them in gas phase. But that is very different from a planetary atmosphere where the chemistry is not happening on any surface. It's all gas phase chemistry, and these molecules are extremely unstable. So the same process cannot be invoked in a planetary atmosphere, number one. Even if you did that, the amounts produced of these molecules, DMS, I think, is the one that has been observed. I don't think DMDS had been observed in that comet. Even if you say that for some magical reason, let's invoke the same process, the amounts produced on these comets of these molecules are extremely low. You can't invoke that to explain the amounts we are seeing in the planet's atmosphere, this planet's atmosphere, which is, as I said, thousands of times higher than on Earth. And finally, you can't even make a delivery argument because these molecules being as unstable as they are, even if you crash like a ton of comets into the planet's atmosphere, they would not make it into the lower atmosphere and remain stable there for a long time. So we discuss a lot of these things in our paper, but I don't think the comet argument works currently. If someone comes up and comes up with a different abiotic argument, it'll be great, because at the end of the day, if we robustly detect these molecules and we can prove that there is an abiotic process that can make these molecules, that's the discovery of a new process right there, right? So I think that would also be a win for science. But currently, based on everything that we know of so far, there is no abiotic process in the literature, at least so far, that can explain the molecules at the level we are seeing. And this is why we think if these molecules are detected currently, a planet with significant biological activity is the only viable explanation. But we also are saying that we need to remain open to unknown unknowns for some other process that may come up in the future.
Which is in itself important because it suggests new chemistry.
Yeah.
And it seems to me that everything about this work says this is new. We're going to learn something from this, no matter what it is, whether it's life or not. But it is interesting because it is the first and best so far, because we've had so few detection of what could be a biosignature. So would you characterize it that way and say that, look, this is the best, this is the closest we've come so far?
Yeah. I mean, in my personal view, and I've said this in many forums, like to me, this is like a transformational moment because it is taking us into the era of quantitative astrobiology, observational astrobiology, right? So if we are able to, this is the first time ever we are even having an argument about a molecule being a biosignature in an exoplanet atmosphere. We never even had this chance. And that's a big deal because all science starts with arguments, but you need data first. And this is the first time we have that data. We have an instrument that's even capable of looking at these atmospheres and detecting potential biomarkers. If not this, maybe there will be some other planet, but at least we have the capability to ask and answer these big questions. So this is why I think like this is a major transformational moment in the search for life, because we have the capability. And if this planet turns out, if these results turn out to be right, then that would be obviously a revolutionary discovery. But even if it doesn't turn out to be life, we have discovered a fundamentally new chemical process that can mimic what life does here on Earth, and that's a big deal too. So either way, I think this is for lack of softer words to capture the reality here, I think we are entering a new era of astrobiology where we'll be now driven by observations, and that's a major advancement in our history.
Could even be characterized as the beginning of astrobiology because it was always a science without anything to study, and perhaps now we have something to study.
Absolutely.
Now, Dr. Madhusudhan, where can people find more information about this and dig deeper into this potential detection of our first detection of an alien biosphere outside of the Earth?
Yeah, so we have just launched a portal on Hycean Worlds, so we can keep people informed about our research in this direction. And if people have questions or would like to contact us in some way, follow us in any way, they can reach us. So we have a website called Hycean. The URL is hycean.cam.ac.uk. So it's hosted at Cambridge. So yeah, so it's got all the information, and we will be posting more updates as we go forward in this research in the future.
Doctor, thank you for joining us today, and I will continue to watch this research with great interest, and I look forward to the next paper.
Yeah, thanks for having me here, John.